All right, let's go ahead and begin. We are live. Hello, everyone. Welcome to a celebration of Margaret Burbidge on July 8th, 2020, 1 o'clock Eastern. On the left there is the ordering of the speakers we'll be having. So thank you all for tuning in and joining today. And we're going to kick it off with Sarah Burbidge.
Hi, everybody. Look, I want to thank everybody so much for putting this on. Frank and Nicole and everybody. I know it's taken a lot of hard work. And I want to thank all the speakers in advance as well. And I want to thank Anneila for the fantastic artwork. I think the stars in her eyes are particularly lovely. My mom would have been humbled and very grateful that you're all doing this. You know, I wish she were able to see it, but of course, you know, maybe she is somewhere in Cassiopeia or somewhere. But I think probably the only thing I can really add to this is a lot of you will be wondering, what kind of a parent was she? Was she a good parent in the midst of all this work? I was actually born right in the middle of all the work on B²FH. And so, of course, there were a lot of babysitters, a lot of nannies over the years, but somehow my parents, my mom and my dad, they made it all work. They were both full of adventure and fun, and they took me all over the world. And I'm a better person for that, I think. And yes, she was a terrific mother and grandmother. In her honor today, in honor of all this, I'm making her old spaghetti sauce. It's kind of an anglicized version of spaghetti sauce, but it's still very good. And so again, thank you, all of you. But the last thing I want to tell you is that on July 12th, the BBC is airing a segment about her on a program called Sky at Night, I think. And I think that one of the things they're going to use is one of her observing logs from 1944. So at the time, she was observing in a small telescope north of London at Mill Hill. And at all of 24 years old, one night, she was setting on Gamma Cas, which most of you will know is the star in the middle of Cassiopeia. And suddenly there were flying bombs coming down around her. And they knocked, the declination went off and she lost the star for a minute. But what did she do? She just reset and kept going. The Luftwaffe at the time was targeting North London, and particularly the Hendon Aerodrome, which is nearby, near Mill Hill. And anyway, she reset and she began observing again. And then she got knocked out a second time, or the star got knocked out a second time. And at that point, she shut down. Well, she kept going for a bit, but then she shut down. But I tell this story just to tell you how much absolute grit she had. You know, I mean, she was very young, and she was pretty frustrated at the time that the war and everything was interrupting her work, you know, and interrupting her polishing off her thesis, which is what she was trying to do. But so I think in this horrible time that we're living in now, I just want you all to think about that kind of grit and toughness in getting through something like that. So that's really all I want to say. Thank you so much.
Thank you, Sarah. I'd like to try some of that sauce. And we will head then to Meg.
Hi, I'm Megan Donahue. I'm the past president of the American Astronomical Society, and after that story, I don't think I can top that. I was going to mention some of my experiences of Palomar, where Margaret Burbidge also observed, and she was the first woman to observe there. She doesn't get the official first woman to observe at Palomar because she observed under her husband's name. And I, I have a funny story to relate to that. I was also a postdoc at Carnegie, and my husband was a theorist at Caltech, and we decided to get clever one year and try to get a slightly a little more 200-inch time by applying for time under his name through the Caltech allocation. It did not work. But I can say that that telescope was primo territory, very, very valued, and it's I feel like when I was driving up to observe at Palomar, I sort of felt like, wow, where did she stay? Where did she spend her time? She certainly wasn't at the monastery. Anyway, the echo of her influence is all over that place and all over observational astronomy. There's going to be a lot of accounts today about Margaret, people who knew her even better much better than I. But I wanted to relate to you some stories from the AAS. Margaret was the first woman to be president of the American Astronomical Society. And the American Astronomical Society had some transitions during her term. One big one was moving to Washington, DC, where they could be closer to the agencies, the National Science Foundation and NASA, and also to Congress to do lobbying. The second thing that happened under her term was also a big change, was that the executive officer of the American Astronomical Society went from an unpaid, basically volunteer position to a paid okay position. Now he gets paid well, but it went from a fully volunteer organization to an organization that now has a professional staff, which I think has made a big difference in the sorts of things that the AAS can do. And my final story is about the establishment of the AAS Fellows Program. The board was thrilled to offer Margaret Burbidge the possibility of being the inaugural American Astronomical Society Fellow, the very first AAS Fellow. And I remember contacting Sarah with a little bit of trepidation because 45 years ago, she had turned us down for the offer of the Annie Jump Cannon Award on the basis of that it was only offered to women. And that sparked a change in that award. It also sparked the establishment of the Committee of the Status of Women in Astronomy. So that particular event, I think, is still echoes in the memory of the American Astronomical Society. But I was so pleased when she accepted the award. We couldn't have been more delighted. And the only thing I regret is not being able to hand it to her in person. So, but I know she got it. I got a picture of it in the mail from Kevin Marvel before he mailed it to her in January. And I really so glad that we were able to honor her that one final time. So in closing, with apologies to my British colleagues, I hope you'll forgive me, but but I think of Margaret Burbidge as our queen, queen of astronomy. And she made her way through all that grit, with all that grit in a field that was mostly male, is still mostly male. And I'm so happy and so grateful to her for having shared her path, even so briefly. So thank you.
Thank you, Meg. George.
Shall I share my screen?
Yes.
Can you see that?
You're good to go.
Very good. So I am George Fuller. I am the director of the Center for Astrophysics and Space Sciences at UCSD. Margaret was the first director. And you might wonder, I just want to say some things about Margaret's contribution in my idiosyncratic view of the history of physics and astronomy, myopic as it might be. I was a graduate student of Willie Fowler in the 80s. And Margaret and Jeff had not been there for quite a long time. However, if you knew Willie, you knew that he loved to tell stories. And many of those stories, if not most of them, revolved around the Burbidges, and especially around Margaret in many ways. And her presence at Caltech, even though she wasn't there and hadn't been there for quite a long time, was still very much in evidence. I am a theoretical nuclear and particle astrophysicist, not an observational astronomer. Nevertheless, I later overlapped with Margaret for quite a long time at UCSD. So I got these two different versions and visions really of Margaret's influence in the world and her science. So I just want to say, from my perspective, she had really she's a towering figure in the history of physics and astronomy over the last century. She had a foundational role in what I would regard as two great revolutions in physics over the last century. The first, of course, was the thing that you all know about, the connection between observational astronomy and laboratory and theoretical nuclear and particle physics. This is a central thing, a central theme in physics now. And I maybe it's because of my idiosyncratic view of the world, having been a graduate student of Willie's at Caltech, but essentially it looks to me like the paradigm for how we operate in theoretical nuclear and particle astrophysics and observational astrophysics now is this marriage between astronomy and the laboratory of nuclear and particle physics. And the paradigm for that, I claim, is B squared FH. What happened in the 1950s with the realization that nuclear physics played a role in stars and the creation of the elements. And of course, Margaret and Jeff were in on that. Margaret was a key part, a foundational part of that whole enterprise, which I think is the paradigm for how we operate now in this field. The second great revolution in physics, I think, relevant for this, for Margaret's contributions, was really the advent of high energy astronomy, X-ray astronomy, and the discovery of QSOs in the 1960s. Of course, there you recognized, I think it was recognized at that time, that you needed non-nuclear sources of energy, specifically gravitational sources of energy. And there was this explosion of research in general relativity and cosmology that came about as a result of that, centering on black holes. And so Margaret and Jeff were heavily involved in that effort in relativistic astrophysics. And of course, Margaret's key contribution in astronomy really at that time and in this problem was really her work on QSOs. Her steady work on QSOs, she added to the discussion of that, as far as I can tell, in a big way. Ultimately, that led, of course, to her being involved with almost a third revolution, which the astronomers know well, which is the advent of space-based astronomy, even optical astronomy. And so she had a tremendous role in the faint object spectrograph, for example, and using that, the faint object spectrograph on Hubble, again, to continue this work on QSOs. And I think Vesa Junkkarinen will talk a little bit about that later. In any case, that work has left us with what I regard as a key outstanding problem in physics, the origin of the supermassive black holes, which power these QSOs. This is front and center in the ongoing revolution right now in multi-messenger astrophysics and gravitational wave astronomy, for example, and astrophysics. Where do these supermassive black holes come from? How are they related to the early evolution, the mass assembly history of galaxies, for example, the nature of dark matter, et cetera, et cetera. So if you look at everything that we do, the really interesting and vital areas in all of astrophysics and physics now, you will find Margaret's fingerprints on it. Thank you.
Thank you, George. Anneila. Anneila, you're muted. And George, you need to stop sharing. There we go.
Done.
Anneila, you're muted. Anneila. Unmute her.
Frank, it's Anneila.
Sorry. Anyway, we are muted and she doesn't know it.
Sorry, I should have unmuted before. I really was trying. My cursor was giving me enormous problems, which it does when I least want it. I'd like to thank everyone for asking me to talk today. I'm assuming that, like George, a lot of people will deal with Margaret's science. I want to talk about her from a more personal point of view, because that she wasn't just an impressive scientist, she was an all-round impressive person. My foundation with the friendship with Margaret and Jeff and Sarah, their daughter, goes back to the early days in La Jolla at UCSD, but also to the many summers where my late husband, Sargent, and I went to Cambridge to be with B²FH and their attendant hordes as part of something that was for a while called the Traveling Circus. And so we went there every summer. But first of all, I think we really got to know Margaret and Jeff and Sarah when Margaret and Jeff invited Wall to come as an assistant professor to UCSD. And I went as a graduate student. They were the most kind and hospitable and wonderful friends as well as colleagues to us. I can't say enough about it. I will say, however, that at that time, Jeff was my advisor for a short time before we went to Caltech. Jeff was my advisor for a peculiar reason. In those days in the University of California, indeed probably everywhere, you could not be a professor in the same department as your husband, or usually that's the way it was. The husband got the professorship, the woman did something else. However, at UCSD, there was a marvelous arrangement already in that Maria Mayer, whom you will mention again, had been made a professor of physics at UCSD, and Joe Mayer was the chair of chemistry. And Joe Mayer made Margaret a professor of chemistry so that she too could have a professorship at UCSD. And I don't know how long it lasted, but it certainly was during the time that she could not be my advisor, which would have been more sensible. However, one of the highlights, and I think I'll remember it for all, I have remembered it all my professional life, is the Sunday afternoon walks on the beach at La Jolla Shores, where there weren't just us and the Burbidges, but there were all of these visiting scientists scientists, their many, many friends. And I want to emphasize how fantastic it was that so many people were known and part of their circle and came and talked about science and had wonderful arguments, although I was usually trailing behind with Sarah talking about something much more trivial at the time. But I did hear, I mean, I was part of a lot of these conversations. It was a wonderful beginning. And having said that, you can see I began to see Margaret in a much more personal light. And quite frankly, Margaret was a role model for me before there was even a thought or a term of such as a role model, because honestly, she had it all, as did Maria Mayer, I might add, in my view. Margaret had a career, she had a husband she adored, and she had a daughter who was the light of both their lives. And for her, it seemed effortless. There must have been a lot of grit there, as we heard, but it seemed to me effortless. And I will say she was also the epitome of cool before that term came into vogue. She was a woman ahead of her time in many, many ways. Now, having said that, I guess I didn't realize at that time, but I've come to realize more and more. And of course, I realize now when I'm thinking about things like obituaries and memoirs, that she did in fact face a lot of obstacles throughout her life. But I think, again, as Sarah suggested, she's a model for us in how she coped with them, because when she entered the field, there were few women, but it would have been a difficult field anyway. But having said that, she actually had the benefit of a family background that made her, probably she was genetic as well, she was a fiercely independent and a surprisingly confident person. And not just saying woman, at a time when I think that she would be surprisingly confident and fiercely independent, even in today's world. When she looked, when she found an obstacle, I think she said throughout her life, if somebody stopped her, she just looked for another way to do it. And that was part of her life. And so in fact, that actually, if you look at the bulk of her career, informed in a way the way she attacked science. I think because of the war, she was, as we heard, observing during bombing raids. She talked about them as if they were just a plain old nuisance by the time I saw her, and undoubtedly they were. On the other hand, she was using a telescope that was regarded as not terribly worthwhile, because the wonderful telescopes that could do photometry were tidied away for the period of the war. So she became a spectroscopist. And of course, by the end of her career, she was one of the world's most brilliant spectroscopists. Even Jesse Greenstein acknowledged in his oral history the special talents of Margaret Burbidge. And I think that was very impressive. That was for me, because of course, Jesse was at Caltech and one of my mentors. But anyway, at every turn, she found a way. So she became a spectroscopist, not just a spectroscopist, a brilliant spectroscopist. And what she did, and you'll see this at every turn of her career, is finding an obstacle. She looked for how to get around it. She wanted higher dispersion spectra. She looked where she might get them. She went, spending her own money, to a telescope in France. She read up around the subject. What were people doing in this field who had better equipment? Well, Struve became person she followed. Struve is at Yerkes. She goes to her first IAU and she meets Struve. Can you all hear me? It's just a phone. She meets Struve. She gets to know him sometime down the road. And please note, sometime down the road, because this is what happens. She has a plan. It doesn't quite come immediately. She goes to Yerkes. At Yerkes, she's lucky again, but she's not just lucky. She's opportunistic. Hiltner is putting a new photometer on the telescope at McDonald. She has no observing time for maybe 6 months, a year. But he says, oh, well, the objects you want to look at, you can go down because I won't have photometric nights. You can go down and use it as a spectroscope. She does. And there we start with a lot of the stuff that builds into rotation curves of galaxies. But I think for today, what I want to dwell on a little more is the connectivity between her being at Yerkes and the University of Chicago being, of course, part of that. Because that's when I think the seeds, if you look at what she's said and what she's written, are sown. She meets Maria Mayer. She goes to the workshops where Mayer and Gamow discuss the magic numbers, for example. She then gets to meet Urey. By the time she leaves Chicago and they go back to Cambridge, she is already thinking that, in fact, what Maria Mayer is talking about, and to some extent Urey, ties in with a lecture that she and Jeff had heard Fred Hoyle give at the Royal Society in the 40s. There's a whole linkage here. They go to Cambridge, they meet up with Fred because Jeff and Fred, of course, have remained close. And then Willie is visiting Fred. And out of this comes B squared FH. But what I want to emphasize is that she was there, the catalyst, you want to call her, but actually I think she was like the creative germ in many ways. She brings together a whole lot of information that gives us in the end V square FH. And what I would like to say, because I've only got 10 minutes, is that if you look through her papers, what is so damned impressive to me is that it's clear that thoughts like what could I do better in the spectroscopy of these B stars? What could I do better in nucleosynthesis? Undoubtedly, what could I do better with massive black holes? Little seeds are sown throughout her career. You can see it in her papers. You can see the turning points as suddenly they reach fruition in an amazingly brilliant creative career. And so I'm probably running ahead of myself, but I think that she just took exactly what she could do and let it lead her further on and came to better and better ideas. It goes on like this. But what I really do hope I've emphasized is her uncanny ability to connect the dots, to bring her past experience to bear on this. And I would say she did this while also leading a family life that I admired greatly. And I saw it up close and personal quite often. As Sarah, we ate dinner, we in Cambridge, there were fun, we moved on. So of course, I'm awed by her as a creative scientist. I think she was a brilliant spectroscopist, one of the most brilliant, not just of our century, I mean, of the last century. But I loved her other side too. I loved her family side. I loved her fun side. She had a very sly wit. And she had a very naughty desire to push any boundaries. And Sarah tells me she could pick locks too. So I will let your imaginations run wild at this point. But honestly, she was a person whom I felt it's a privilege to have known her and to have seen her at work and to be part of her life in such a minimal way. For me, I can't thank her enough for just being. So thank you for asking me to talk.
Anneila, thank you so much. And next up on
I managed to get here, sir.
All yours, Virginia, go ahead.
Shall I go ahead?
Please do.
Okay. Good morning, afternoon, or evening, depending on what time zone you're in. We're here because we all knew and very much liked her. Loved Margaret. We wish we could have known her better. So go read her own autobiography and annual reviews and Jeff's. Then go read her oral history and his, done in 1978 and 1977 with David Dvorkin and on the web of the American Institute of Physics. Margaret and I had something in common. Our fathers were both chemists, good ones. Her father was a better businessman, and his patents, including rapid vulcanization of rubber, made a middle-class lifestyle possible for her mother and the two daughters after the father died. The tipping point, I think, was her going to University College London. She could have gotten into Oxford, Somerville, or Cambridge, Newnham, Girton, but UCL had an observatory available to undergraduates she could observe. And she had an advisor, an unlikely chap named Clive Gregory, who went off to war eventually. We'll come back to that. There was also already another woman on the staff, at University College, Elizabeth Williamson. Her title was Honorary Assistant, and she appears in the annual reports of the observatory from 1926 onward, doing radial velocities, joining the eclipse expedition, and so forth. So one piece of advice I give to students is wrong. I tend to tell students, go to the best place that will take you. That isn't always the right choice. Margaret would have done much less well, I think, with Eddington at Cambridge or with what's-his-name at Oxford. Her first degree, she and her mother both felt she should get a job. So she applied for and was offered a job working with Leslie Comrie. Leslie Comrie is another Cambridge product who was one of Cecilia Payne's best friends, but eventually he left the Naval Nautical Almanac office and started a small company to do tables for the British government. The war is about to start. She has one lunch with Comrie and flees back to graduate school. Comrie did us a major favor by sending her back to graduate school. I'm not exactly sure what happened at that lunch. It isn't quite in the oral history, but you can kind of imagine. So there she is back at University College where she meets Geoffrey Ronald Burbidge after the war. Meanwhile, she's joined the Royal Astronomical Society. She starts going to talks in London. 1941, she hears Eddington speak. She describes him in her oral history as a crabby little man who looked in the corner of the room and gave bad talks. This is not the Eddington that Cecilia Payne fell in love with, but it's the Eddington, I think, already a few years earlier, who tried to knock Chandrasekhar out of the running for anything by saying that his idea of relativistic degeneracy was nonsense. Meanwhile, yes, she was impressed by Milne, actually. She never met Jeans. The book that was most important to her in youth was actually one on the universe by Max Born. They spent 5 years, as you've just heard, at Yerkes Chicago McDonald, and she collected lots of spectrograms. Curiously, she never appears in Chandrasekhar's autobiography that covers that period in great detail. Jeff is mentioned in one sentence to say that Burbidge has arrived, but it's Jeff, not Margaret. And then she goes on to UC San Diego. They go on to UC San Diego. And you think, finally they found two good positions with access to good telescopes. Not quite. The director at Lick in those days was Albert Whitford. He brought the 120-inch online, which was a very good thing to have done. On the other hand, he felt that time at Lick should be reserved for the people on the Lick staff at Mount Hamilton, grudgingly allowing people at Berkeley to observe. Well, UCLA started hiring astronomers. Santa Cruz started hiring additional astronomers. Whitford became very angry and wasn't at all sure that it was going to work to let Margaret from San Diego apply for Lick time. Actually, her earliest papers from that period use the spectrograms from McDonald, and it's a year or so before she's reporting with Lick data. Eventually, Whitford decides, okay, UC San Diego is an astronomical campus, but nobody else could use Lick as a recruiting tool. 1984, Whitford does an oral history. 1984, 12 years after Margaret has arrived at UC San Diego. And he says there are 4 campuses with astronomers: Santa Cruz, Berkeley, UCLA, and UC San Diego. I was by that time a full professor at UC Irvine. Am I an astronomer? Not to Whitford, apparently. We now actually have astronomers on all our campuses. And as you may have heard, we've just announced our new campus-wide, university system-wide president, Michael Drake, who was here at Irvine for some years. So, apart from all her other firsts, she almost broke the tyranny of Mount Hamilton's staff. Meanwhile, she moved from observing stars to galaxy rotation curves, worked with Pendergast as well as with Jeff, and at Lick on to quasars. She held the record for largest redshift for something like 6 or 7 years, co-discovered absorption lines in quasars. Adventures in directorship. The Brits invited her to come be the new director of Royal Greenwich Observatory when Richard Woolley reached retirement age. She told them that Jeff would make a better director. And I think his 6 years at Pitt Peak demonstrated that this was almost certainly true, although it ended in a bit of a mess for complicated reasons. But she took the job. She was there in England for about 15 months. It did not go well. The chaps in charge still were Richard Woolley and the new Astronomer Royal. She didn't get to be Astronomer Royal, the first director of RGO not to be. The new Astronomer Royal, Martin Ryle, did not like Jeff. Ryle had not liked Jeff for many, many years since they spent time themselves in Cambridge. She didn't like the Astronomer Royal for Scotland, Herman Brooke, which I don't understand. Brooke's second wife, Mary, was another lovely woman and was herself an astronomer. Anyway, many things went badly. Sarah didn't like it there. The job that Jeff had been promised didn't materialize. She broke her leg returning from a nephew's wedding. Nephew? Well, yes, remember, she had a younger sister who did not go to college. She became a Wren, a Women's Royal Navy auxiliary during World War II. She broke her leg, spent weeks in hospital, was discharged with careful instructions how to use her crutch to keep from hurting the leg that had been broken. They told her to favor the wrong leg. It took weeks and weeks to discover that. The bottom line is she held out for 15 months and came back to UC San Diego. Very sensibly, neither of them had resolved their jobs or resigned their jobs. They'd simply asked for leave of absence. That was a very good choice. Jeff, going to head up Kit Peak, made the mistake of resigning his position at San Diego, and so had to return as emeritus. He was never reappointed at UC San Diego. That Margaret was a good administrator, in addition to all the other things that Anneila said about her. It took me 2 minutes to recognize Aneila's voice because I missed the introduction. The system wouldn't let me in. Okay. In addition to everything else, she was, in fact, a very good administrator. San Diego became the principal investigator organization for one of the Hubble Space Telescope instruments. It was required that they have an organized research unit. Notice that every one of those words is somewhat optimistic for what actually happened. But she became the director for something like 6 years of the Center for Astrophysics and Space Science at UC San Diego, eventually succeeded by Larry Peterson. But she was a very, very good director, it turned out, in what had become her home country. Oh, she took out American citizenship when she was elected to the presidency of the AAS and coped with the APJ being declared a commercial organization. She coped with not being allowed to meet in states that hadn't okayed the Equal Rights Amendment. She refused the Kennan Prize and made the AAS reorganize that. But she was, in fact, a very good administrator. I have a second lesson in addition to the best place that will take you isn't always the right choice. Our second lesson, we go back to University College London. Gregory, in fact, did not have a PhD. Margaret was his only student. Am I qualified to talk about World War II stuff? I'm old, but not quite that old. For even the senior participants in this gathering, there's a generation between us. But my late husband, Joseph Weber, served on active duty throughout World War II, first on the aircraft carrier Lexington, and after she was sunk, he skippered a submarine chaser called the SC-690. But as a result, I know something about celestial navigation and what it was that Gregory was doing for the Brits during World War II, trying to work out how to navigate close to the poles, because the altitude of the North Star and trying to get an altitude for the sun, particularly during the northern winter, doesn't work very well in polar regions. So he was working secretly on polar navigation. That left Margaret pretty much to run the observatory, but she also did war work. She assembled rangefinders and put together the glass plates to be used for aerial reconnaissance by putting little dots of transparent and opaque materials in the right places. So they were all doing war work. But in addition, she completed the thesis on, as you heard from Anneila, Gamma Cass. Vera Rubin very early worked on Gamma Cass and loved the idea that it was Margaret's star. Now, was spectroscopy of Gamma Cass a good choice in 1941, 42, 43? Yes. In those days, stellar spectroscopy, which led up to B squared FH, was indeed a hot topic. This is of exceeding importance. What you do for your thesis lives with you through your first job, through getting tenure or not, through winning prizes or not. And I think there is evidence that down into modern times, meaning what Anneila and I, at least, and maybe even Meg, remember firsthand, women did not always get very good thesis topics. I can come back to that if there's time. But Margaret, as it happened, had a very good thesis topic. And this carried her forward through first stars, then rotation curves, though they knew they were not seeing the outer regions, as she did not discover dark matter. But Vera Rubin interned with the Burbidges and did more extended rotation curves with photoelectric detectors a little later. And then, of course, Margaret moved on to active galaxies and quasars. Her own views on cosmology, read her own, again, her own autobiography and annual reviews. She was not persuaded of standard hot Big Bang, I think, at any point. But she did a hot cutting-edge thesis, and that was a good thing for a gal breaking into guys' territories. I think we need, this is my second lesson, I think we need to think about that now, as and when we try to diversify with underrepresented minorities in our own graduate programs. I think we need to make sure that their thesis topics are indeed forward-looking, hot, current, and this will make a significant difference to what happens to them. The Caltech example, I have 30 seconds, I think. The first two women who got degrees there, their thesis work was never even published. The next two, our theses were sent to AJ, the less prestigious organization. It was only the last two gals who got PhDs in this cluster, Anneila and Judy Cohen, whose theses were published in the prestige journal, the Astrophysical Journal. Caltech did learn, Uncle Jesse did learn, it just took them a while. But I think this is one area where we need to think hard as we try to diversify our community to make sure that underrepresented minorities do theses that will carry them forward. Margaret had one female PhD student at UC San Diego. Her name was Donna Womble. Her name still is Donna Womble. She came to UC San Diego from UC Irvine, and she went on with double fellowship to Caltech, and then she went into industry. But I suspect she's paid more than all the rest of us put together. And what else do I want to say? I have some notes here, but I can't read them. It doesn't matter. Oh, yes, there will be a long obituary of Margaret in the October issue of Observatory magazine. And I know it's good because I wrote it myself. Thank you very much for your attention.
Thank you, Virginia. Thank you. Fred.
Yes, hi everyone. Thank you for inviting me. I'm Fred Hamann. My relationship with Margaret began when she hired me as a postdoc in 1993 to join the Hubble Space Telescope Faint Object Spectrograph team that she was leading at UCSD. And then I remained there on Margaret's team until 1999 when I left to join the University of Florida. These were really exciting times. HST had just launched in 1990 with FOS on board. So this was a major turning point in all of astronomy, pushing new frontiers. Early science from the FOS was coming in, including things like the first conclusive evidence for a supermassive black hole in M87, along with a measurement of the mass of several billion suns. Margaret and her FOS team at UCSD were providing advice to the Space Telescope on observing procedures and calibrations and working frantically on new data and new scientific analysis. And they were writing numerous papers of all the early science results that were coming out of HST, focusing mainly on quasars, distant galaxies, but specifically quasars, quasar absorption lines, quasar outflows. And meanwhile, while all of that was going on, the Keck Observatory had just begun full science operations in 1993, so there was a buzz of activity at UCSD, and thanks to Margaret hiring me, I jumped into the middle of it. And it turned out to be the most productive time of my career. Margaret and the rest of her team at UCSD, including Vesa, who you'll hear from next, I guess, were very welcoming and very helpful to me. Margaret had a very quiet but commanding presence. She was extremely knowledgeable. She wouldn't always let on to the extent of her knowledge of things. It was sort of, she was quiet, but extremely knowledgeable about everything from the politics to the science we were doing. She offered insights and advice every step of the way for me. But her main focus that's really surprised me. Her main focus at that time was making sure that we had what we needed, that we had access to the telescopes and the data and other resources so that we could be successful. She was the most generous and selfless scientist I've ever met. She would always ask how I was doing, how things were going. She even asked me if I was happy. This was my third stint as a postdoc, and I'd been through graduate school, and no one had ever asked me if I was happy. And she meant it. It was amazing. Before arriving at UCSD, I knew Margaret, obviously she's famous, but I didn't know that much about her accomplishments, and I didn't know her at all. But while I was there, we became friendly, and Margaret and Jeff would take us out to dinner. They would invite us out to dinner, or they would have us over to their house. And this was always a lot of fun. Jeff would tell stories about their lives and careers. Jeff would usually do most of the talking. And he loved to talk about Margaret. He was very proud of Margaret, and he was very proud of her, and she was incredibly modest. She would even try to shush him sometimes when he went on too much about her and her accomplishments. He would talk about things like the early days at Mount Wilson and Palomar, where Margaret had to pretend, you probably all know these stories, but where Margaret had to pretend to be his assistant in order to get access to the telescopes, when in fact, she was leading the work and doing all the work, and he was her assistant. He had a general knowledge about the science, but he was, while she's observing and running the telescope and doing all the work, he's downstairs processing the photographic plates. So he was working as her assistant. It's kind of an amazing thing. And keep in mind, building on what Sarah said about her determination, these were the days of macho astronomy. Women just didn't do things like this. And he would tell stories about how she would ride around at prime focus, at the top of the Palomar telescope all night long in the freezing cold in the winter. Just kind of amazing. Jeff would tease Margaret about how many honorary degrees she had, which was, I don't know the exact number, but it's in the teens. It's a large number. And he had received none. But he would complain about this, kidding, and say things like everybody loves Margaret. But he enjoyed being sort of the louder, abrasive one, and Margaret was just amazing and wonderful. So I was amused and fascinated by all of these stories, and I learned much more about Margaret from Jeff's stories than I learned from Margaret herself. But it got me, inspired me to read more at that time about Margaret and learn more about her and her career. And it was then that I finally started realizing what a trailblazer she was. And I'm still learning more, and it's just amazing. I mean, some of these things have been mentioned, but she was the lead author on that B²FH paper, and Jeff would go on and on about her contributions to that paper and how critical she was. She was the first woman director of the Royal Greenwich Observatory, the first woman astronomer in the National Academy of Sciences, the first woman president of the AAS, the first director of the Center for Astrophysics and Space Sciences at UCSD. This had happened before I arrived. She received the National Medal of Science from President Reagan. I mean, learning all about all of these things just made her kindness and her generosity even more amazing to me. So I just, it's hard for me to sort of encapsulate what I feel about her, but she was a remarkable scientist and a remarkable person. And I just feel very lucky and privileged to have worked with her and to have known her. Thanks.
Fred, thank you. Vesa. You're muted.
Can you hear me?
Good to go.
All right. Thank you for inviting me to this online symposium. Margaret Burbidge was my dissertation advisor. And then I came back to UCSD and I worked for many years with Margaret on a large number of research projects. And so I went observing with her many times. So I'm pretty familiar with Margaret and her work. I first met Margaret in the fall of 1976 when I was a second-year graduate student in the physics department at UCSD, and I was looking for a research group with which to do research and get a job as a graduate student. And I was lucky enough to be taken in by Margaret and her research group doing astrophysics. I remember my first observing run on a large telescope that was at Lick Observatory on the 3-meter telescope on Mount Hamilton. And I went on that observing run with Margaret and Gene Smith, who then was Margaret's postdoc, and he later became a faculty member at UCSD. And so Gene and Margaret and I observed quasars. We were doing spectra of quasars. Margaret had moved on from the prime focus spectrometer to the Cassegrain spectrograph and a more sensitive detector. And so we did spectra of individual quasars, and we worked on a program to identify radio loud quasars. And so it was an interesting program. Sometimes the proposed identifications that were sent to us by Cyril Hazard from Pittsburgh didn't work out. Sometimes they were stars, and sometimes they did indeed turn out to be a radio loud quasar. So it was kind of an interesting program. But we would always move on to the next one quickly. Margaret liked to be efficient, and so if things didn't work out, well, she'd go on and try the next one. And even if it was bad weather, we would should still be optimistic. We'd always get ready for observing, no matter what the weather report looked like. And we spent a lot of time checking out the weather. So I started observing quasars on my own after learning a lot about observations with Margaret and the group of astronomers she had working with her. I started observing a peculiar type of quasars with gas flows. These were broad absorption line quasars. And she had observed these many years before, but now we could get better spectra of these objects. And that became my dissertation topic. And I graduated in 1980. I went to work at Kitt Peak National Observatory for 5 years as a postdoc and then as a support scientist, and then came back to UCSD. I applied for a job with the faint object spectrograph team there under Margaret. And the faint object spectrograph project, and in fact CAS came about because in the 1970s, and when I was a graduate student there was an active group in the physics department that worked on instruments for spacecraft. And this was under Carl McElwain and two of his students, Ed Beaver and Richard Harms, who later became research physicists. And they were working on an instrument for the Hubble Space Telescope, the faint object spectrograph. And Margaret was included in this group as an observational astrophysicist, as well as other observational astrophysicists at other institutions. They proposed for this instrument with Richard Harms as the PI, and surprisingly, they were awarded the contract for this. And so that started the era of the faint object spectrograph at UCSD. And the instrument was built by the physicists at UCSD and Martin Marietta. And Margaret had a group of astronomers get ready for the early observations, as well as helping people work on the FOS. And so they hired me at the beginning of 1986 to work as part of that group. And unfortunately, at the beginning of 1986, there was a Challenger disaster. and that delayed the launch of the Hubble Space Telescope by a number of years. It wouldn't launch until 1990. But the group there, the FOS group there, was kept intact, and we worked on preparations and setting up a manual for the FOS and the ground-based observations to support the FOS observations in other ground-based projects. There was a really active time, a lot of collaborations and a lot of sharing of data and working on projects. I was there for the duration of the FOS program starting in '86, and another long-term physicist there was Ross Cohen. And so we were part of that team that Margaret had assembled. And at the time, in '86, she had 3 graduate students, Wei Cheng, Donna Womble, and Tom Barlow. And they all worked on quasar spectroscopy, or the spectroscopy of quasar absorption lines. And so it was a really busy time. Margaret's interest in spectroscopy has spread to all these people, and she was a pioneer in the spectroscopy of these objects. And as you already heard, one of the radio-loud quasars that she worked on finding held the record for the highest redshift for a long time of the quasars. Then finally in 1990, it was time to launch the Hubble Space Telescope, and the FOS team, a large part of the FOS team, headed to Melbourne in Florida for a team meeting and to watch the launch of the Space Telescope. And we all assembled in one of the viewing areas a ways from the launch pad. And we watched the countdown get closer and closer to 0. And then unfortunately at 90 seconds to liftoff, they scrubbed the launch because of a technical problem with the shuttle Discovery. And so everybody went back to their home institutions. And then 2 weeks later, a smaller group of us, including Margaret and me, came back to Florida, and we saw the successful launch of the Hubble Space Telescope. And we were all happy that the Space Telescope was on its way into orbit. And after all these years, the astronomers who'd been waiting to use the telescope and the instruments would get the observations. Unfortunately, a little while after that, we found out that the Space Telescope main mirror had been incorrectly ground, and that meant that there was a large amount of spherical aberration. And for our instrument, the FOS, we would only get about 10% of the light through it that we thought we would get at the beginning of the what it was designed for. And so that meant that we would need longer integration times and we get less objects. But still, the period between 1990 and the refurbishment mission that put in corrective optics in late '93 was a productive one. And we were able to do observations that combined ground-based astronomy and spectra from the Hubble Space Telescope. And then, of course, after '93, things were even better. The Space Telescope yielded a lot of good spectra of quasars. We still were working on quasars. And it was one of the most popular or the most popular instrument on the Hubble Space Telescope for a long time until early 1997, when it was replaced by a more capable instrument. And of course, as Fred has mentioned, at this time, the Keck telescope came online, and Margaret started using the Keck telescope. Early on, we would observe from the almost 14,000 foot level on Mauna Kea, and Margaret would go up to the telescope, and she did fine at altitude. And so it was interesting work. I think I'm not going to go on much longer. I do want to say that the happiest I think I saw Margaret was when she was working and it was clear and everything was going well. She was just one of those people that loved doing astronomy, and that was the main part of her life. And the other things like the politics of astronomy and so on weren't as important to her as doing the work. And she always encouraged us to keep going on our projects. And so I'm really, I want to thank everybody for inviting me to this talk, and I'll always remember Margaret as a great friend. Thank you.
Thank you, Vesa. Next, we have a contribution from Amanda Karakas, and this is a pre-recorded contribution because Amanda is down under.
So I was really pleased to hear about this online event in honour of Margaret Burbidge. I think it's fantastic that she's being honoured in this way. And I was really happy to receive an email from Frank Timmis and Nicole Vassh asking me to make a contribution to this online event in particular. So this talk is a little bit of a musings for me. It's about Margaret's contribution to my field, and also her importance as a role model in physics and astronomy. So I think, Margaret was especially important, at least toward my field, because she helped establish the theory that the chemical elements in our universe were formed inside stars. Now, beside her many formidable scientific achievements, Margaret also challenged various forms of sexism in astronomy, and she held many important roles, including being the first elected female president of the American Astronomical Society. Now, I think more people will talk about that aspect of Margaret's life, perhaps, but I really want to focus more on her science and how her science relates to the science that I do today. Margaret was, of course, the first author of the seminal paper Burbidge, Fowler and Hoyle, probably one of the few papers that we recognise just by the first letter of the authors, B²FH. This was published in 1957, but it was really the culmination of years of work by each of the four authors. And as we know, Margaret's contribution was to gather observational evidence in support of Hoyle's theory that elements were formed inside stars. I think it's really hard for me to put myself into the mood of the 1950s, to imagine what it would have been like to, at least where the prevailing thought at the time, especially in the early 50s, whether the elements were formed mostly in the Big Bang. And I think that these two papers, both B²FH and the paper by Al Cameron published in the same year, they really helped, I think, change that tide and cement the idea that elements, except for a few light elements, were formed inside stars by various processes. And of importance for me, Margaret's paper, so this paper that was led by Margaret, they gave us the lettering notation, and also they gave us ideas for the synthesis of heavy elements, those heavier than iron. And these, of course, are the S process and the R process. Now, Margaret was not a mentor to me. I only met her once. I met her in 2007 at a conference held at Caltech at the 50th anniversary of B²FH. So this was an amazing conference. I met a lot of really amazing astronomers and physicists at this conference, but I also met Margaret. And I think what struck me most about Margaret at this conference was her importance as a role model. All the women at this conference wanted to meet Margaret and have their photo taken, and I was no exception, as this photo on the left-hand side shows. So she clearly meant a lot to a lot of people. And I think if we think about the landscape of physics and astronomy, especially the undergraduate and high school curriculum, there are very few females mentioned. And I know this is changing. So certainly astronomy texts are trying to highlight the contribution of women in astronomy. But certainly when I went through high school, I don't think there was one female mentioned in terms of contribution. And in fact, even today, the Australian high school curricula, both in the states of Victoria and New South Wales, don't even mention Marie Curie at the high school level, and they do teach radiation. So I think it's really important that we highlight people like Margaret and make it clear that there are clever and really important women who contribute towards our field. This conference, I have another funny, I guess it's a funny memory from this conference. Even though this was in honour of B²FH, and this is a paper led by Margaret, it was highlighted at the conference that there were very few female speakers. In fact, it was mostly male speakers were asked to talk. And I was asked to give an impromptu talk about nucleosynthesis in low and intermediate mass stars at the last minute. And so this struck me again, it was one of those kind of ironic things. This is a paper led by a woman, and where she made really important contributions to the paper. But again, it was kind of the role of women, and and having equal or at least trying to have a representative gender balance was somehow neglected, I think, until the last minute. Anyway, so that was just a funny memory I have. The rest of this talk, I'd like to focus just briefly on the origin of heavy elements. And of course, this is the field that B²FH laid down the foundations for the synthesis of elements heavier than iron. Now, they noted 3 processes I've listed to here. So they listed the P process, rapid proton capture process, for making elements heavier than iron, the rapid neutron capture process, as well as the slow neutron capture process. So it's these latter 2 processes, the R and the S, that form heavy elements via the addition of neutrons. Now, I've done a lot of work primarily in terms of the S process, so this is an area that's very close to my heart. And I don't want to dwell too much on the details, but just to note, if we look at the state of this field today, at least pictorially, I think we can say, I think, that we've made significant advances. And I think both Margaret and all the authors would be very pleased to see that we've finally put the R process on firm foundations. With the significant achievement that we now know at least one of the sites of the R process. Maybe there are more, but we know that neutron star mergers are a source of heavy elements now. And I think this was a really phenomenal achievement. In terms of the slow neutron capture process, we've also, I think there was a lot of evidence even in the 50s that low mass stars make heavy elements. The discovery of technetium by Merrill in 1952. But also, I think there was a lot of evidence that there were lines of heavy elements in the atmospheres of these low mass red giants. Now I think we have firmly established, both theoretically and observationally, that low and intermediate mass asymptotic giant branch stars, so the final phase of stellar evolution, that these low mass stars make a significant contribution toward heavy elements. But we also know that there are other sources of S-process elements. In fact, they can be made any time we have neutrons formed slowly, for example, in hydrostatic phases of massive stars as well. We think that the R process and S process contribute about 50% each as well now toward those elements heavier than iron. However, there are still observations today that are not easily explained. So there are puzzles that perhaps go beyond the S process and the R process. And in fact, I think B²FH focused on the S process and R process because they are the two extremes of neutron capture. The S process operates under conditions of low neutron density. And this is an area that can even be tackled somewhat analytically. And it did it, and it could be at the time. For example, Clayton went through it in his textbook. The R process, of course, is the other extreme where you have very high amounts of neutrons. But there's no reason that nature only operates at the extremes. But we didn't really start discussing the I process, an intermediate neutron capture process, until 1977 by that first paper by Cowan and Rose. And even then, this field stayed very quiet until until the 2000s. And it's only been in the last possibly 10 years or so that we've made significant progress in understanding what an intermediate neutron capture process looks like. We still are somewhat unsure of what the sites of the intermediate capture process are, although we are making some headway. Some of the observations, for example, are carbon-enhanced metal pole stars that have enrichments in the S process element, barium, and elements and enrichments in the heavy R process element, europium. And so this is an example of a low metallicity carbon-enhanced metal pole star that shows such features. This star cannot be really reproduced by laying down an R process foundation and then putting an S process on top of that. And in fact, all these carbon-enhanced RS stars, let's call them carbon-enhanced I stars, they really they really are better fit by an intermediate capture process. Now, this is a star that's not self-enriched. It's a low mass star. It exists in the halo of our galaxy, and it was polluted by another source, or it was formed out of material that was polluted by something more massive than this star. Now, there are also, so along with these carbon enhanced metal poor stars, there are also post-AGB stars of high metallicity in the Magellanic Clouds of our galaxy that also show enrichments that are better fit by an intermediate neutron capture process. These stars are self-enriched, so it perhaps tells us that low mass, low metallicity, low mass stars can sustain an eye process under very specific conditions, perhaps if there are proton ingestment episodes. Now, this is a paper that was, so there was a paper by Melanie Hampel that was published last year, and I have to say, so this was a female majority paper where we're exploring really beyond the S process, if you like. And we dedicated this paper at the time to the celebration of Margaret's 100th birthday. As you can see at the bottom, this is just a capture from ADS. I've also been involved in recent work looking at the origin of elements with cosmic time. So this is the process of galactic chemical evolution. And I've been involved in a study with Chiaki Kobayashi from Hertfordshire and Maria Lugaro. And we took the theoretical yields from all sources that make heavy elements. We didn't include the eye process in this because we don't still know what all their respective sites are. So they may be formed in a number of different sites, maybe accreting white dwarfs. This is work that Falk Herwig and his group have been looking into. They might be made in post-AGB stars or even low metallicity, perhaps maybe low metallicity massive stars. There's a number of different sites that may sustain an eye process, but we have left them out of this study. We really focused on the contributions of the S process and the R process. And for the R process, we took theoretical yields. We're not taking a 1 minus S approach here. So we're really trying to be quantitative here with our yields. And we are looking at the evolution of elements from carbon through to uranium. Now, I don't have time to go through all the details. I just want to focus on one of the elements, and this is strontium, which has an important S and R process contribution. So we can see that the strontium to iron is a function of iron to hydrogen. So this is a proxy for time. And we can see the S process contribution can match the solar abundance at the solar composition. But we see that in the early universe, unsurprisingly, strontium is a majority R process element. I focus on this element because I really want to highlight that the S process alone can match the solar abundance. We don't, and in fact, the S and R process alone together can explain the evolution of this element. We don't need any other processes such as a light element primary production for strontium, at least in our paper. Now, as I said, I don't want to dwell on I don't want to go through this paper in too much detail, but I just want to focus. This is a female-led paper with myself on the left-hand side, Maria in the middle, who is actually the shortest, even though it's not obvious from this photo, and Chiaki, the lead author, on the right-hand side. And just similar to the paper from last year, we also dedicated this paper in the acknowledgements to the late Margaret for all her, for her important role as, for encouraging women in nuclear and astrophysics. And I think that's a really good place to end this talk, just to highlight Margaret's role and how she has influenced a lot of us, and she, I think, provided a lot of encouragement. So I hope the rest of this online event goes really well. I'm sorry I can't be there in person, but it's very late in my time zone, and so I can't be there to answer questions. But I hope to listen in on the recorded talks later.
All right. Thank you, Amanda. And Artemis.
Can you hear me?
Yep.
Let me share my screen. Looks okay.
All good. Take it away.
Okay, well, thank you very much for inviting me to join this event. I sadly never met Margaret, although obviously I know about her work and I always admired her as a role model, as one of the first women pioneers in astronomy, But also the B squared FH paper for the field of nuclear astrophysics and for stellar nucleosynthesis. Obviously, anyone working in this field, it's a paper that I asked all of my students to read, and every once in a while, I go back and reread it, and I'm more impressed every time discovering all the details that they got them all right at that time. So in this talk, what I'll try to do is kind of make a connection between what was the physics that was described at the time with B squared FH and a couple of examples of the new discoveries or the new research directions we're taking today and how they're linked. There's a lot of overlap with Amanda's presentation, the science Amanda just presented. But this one, like in B squared FH, where you have the combination of astronomers with modelers, the theorists and experimentalists, this is again the same thing. So Amanda is more on the astronomy side and I'm more on the nuclear physics side. So this is a slide literally copy paste from almost every single talk I'm giving. It's when you talk about stellar nucleosynthesis or nuclear astrophysics, you have to show all these processes, and as a nuclear physicist, you have to put them on the nuclear chart. So if there's non-experts listening in, this is a chart that we nuclear physicists use to plot everything. So every box is a different isotope here, where the vertical axis is increasing proton number and the horizontal axis is increasing neutron number. And so already at the B squared FH paper, what they were trying to do is kind of explain this abundance distribution that we see at the top left panel, how the different elements are produced in the universe in different amounts and why, and can we have models that explain every single element in this picture. And so all the different processes you already heard about from Amanda, we put on this chart. And so the kind of the normal stellar evolution with the different burning stages and so on, that bring you all the way to iron, are marked here as the burning stages. And this would make kind of these lighter elements. And then for the heavier elements, what they had already were these two neutron-induced processes that you heard about. Is the S for slow and R for rapid process. And they also introduced a P process, which is responsible to make these isolated proton-rich isotopes that cannot be made with the other two. So all of this was already there. And I went back and grabbed some pictures from that paper because I wanted to really see the correlation and how things have changed with the picture we have today compared to what they had before, what they had at that time. So this is the same abundance distribution I showed on my previous slide, and this is from the original paper. And I grabbed a table that I find amazing, that qualitatively they tried to describe every feature in this picture, and they got every single one of them, all the important pieces at least. And so they already say, I won't go through everything, but they already say that initially you have this exponential decay all the way to mass 100. And that probably leads us to believe that these elements are made in kind of the stellar evolution, the different stages of stellar evolution. But then above mass 100, then it's kind of flat. And so this probably means that the neutron capture cross sections are probably constant, and also that there's some cycling going on in the R process. This is one of the open questions still today about how cycling happens in the R process. And again, for the non-experts, if you're not familiar with the term, it would be that as the R process progresses and builds heavier and heavier elements, at some point you build so heavy elements that you could have fission and kind of feed back, the nucleus breaks and you feed back the lighter masses. And if you keep doing that a few times, then you create kind of a robust distribution of the elements. So yeah, I can keep going. They talk about this group down here that is not very well produced, and they call this the X process for what kind of mechanism could produce those lighter elements and why they're so low compared to the other elements. We heard earlier about Maria Gepermeyer and and the magic numbers. And so they made the connection already between these peaks that show up in the R and the S process and how these connect directly to the nuclear magic numbers. This is just an amazing connection, the one-to-one connection between nuclear physics, the basic properties of nuclei, and this stability with the magic numbers, and how they show up as abundance features in the observations, and so on. So you can see, you can go back and you look at all these features, and it's just impressive how they put it all together. A lot of it was their own work done independently, but then the four come together and they bring this, and they created this amazing big picture. And again, a couple more examples of what from the original paper. They had graphs that show reaction flows in different directions. This is way too much information even in one plot, but again, they show all the different reactions and how things could evolve. And even timescales, how the R process must be an explosive process, and the same for the P process. Otherwise, you couldn't have the features that you see, and so on. So this is again, every time I look back, I get impressed and I get excited about these contributions. And so what I wanted to bring today is make a connection, make a connection with what we're doing today. So obviously at that time, they didn't have the fancy computers we have right now, and a lot of it was done qualitatively, or it was done on paper. And so today we have simulations that show exactly how the reaction flow goes in different processes, and you can observe features, you can change parameters, you can change the nuclear physics input or the astrophysics input and see how this distribution changes. And I have one example here. This is made with Skynet by Jonas Lipner. This is kind of how this goes. You can see here with the color, the population of different isotopes, again, on the chart of nuclei. Stable isotopes are in these boxes. And you see how this R process evolves very quickly. This is an explosive process and goes very high in mass. And at some point when the event is over, then everything just slowly decays back to stability. And up until recently, the only thing we had to use in order to explain or to understand how an R process works is what's left behind. So after all of these isotopes decay back to stability, then we would look for the abundances in stellar observations and just see how these distributions, how the distribution looks like, and try to create models to reproduce that. But another amazing discovery that happened recently is, of course, the gravitational wave discovery and the electromagnetic observations that came along with that. So again, for the R process, the big question for a long time was, is it happening in supernovae, or is it happening in neutron star mergers? This is a new thing, a new discovery that was not obviously known in the 1950s. But yeah, the gravitational wave observations and the electromagnetic observations showed different behavior that is exactly what I described before. When all of these isotopes decay back to the stable isotopes, they produce signals. This is radioactivity. And if you have a lot, you can't see when it's one of them, but you have so many of them happening at once in such a big event, then you can look at the distributions. And this was the first confirmation that neutron star mergers could be the site for the R process. So this is just to show you one example of, this is big questions that we had from the 1950s, and even today, this is an open field of research, and we're making new discoveries every day. On the nuclear physics side, I'm a nuclear physicist. There's a lot of nuclear physics input needed in these calculations. So we look at the observations and you get whatever observation, whatever signal you get, but then you have to go back and interpret what that means and try to understand what was happening inside the star. So you need to use all the nuclear physics that goes in it. And there's a lot. And most of it, for the R process at least, we don't know right now. So this picture here shows in the darker colors isotopes where we know some of their properties, definitely not all of them. And the R process path is this blue line here. And it's not, again, we don't know exactly the R process path either, but that's roughly where it is. And there's not a very strong overlap between what is known already and where the R process would take place. And that's why, again, as nuclear physicists, we are very excited about the next generation facilities that will give us access to these isotopes. And for example, you can see the line here that is the next generation US facility, FRIB, that I'm going to mention in my last slide. So that was one example for a process that B²FH did introduce already, but there's still a lot to learn about. There's also, Amanda mentioned this before, there was also a process that they didn't introduce at the time, and that was because they didn't need it. So the observations, the abundances they had at hand at the time didn't need an additional process, so they didn't have anything to explain. And this came a lot later. And this is one example from Falk Herwig's group in University of Victoria in Canada, where they collected a lot of observations. This is different elements plotted here. And what they showed is that if you would have an S process, you would expect these abundance ratios to show up in this green box. And if you would have R process, you would expect these isotopes to be right around this blue box. But there are a lot of stars that have different signatures. And this kind of prompted the need for an additional process. And this is what's called now the intermediate process. And again, a lot of us are very excited about trying to interpret this, trying to see what is needed to understand. The site is not yet known. So there's a lot to learn about this, this process. And on the nuclear physics side, this is closer to the value of stability. So the open squares here are stable isotopes. So the I process kind of goes closer to the stable isotopes. So they're more easily accessible even by current facilities, but there are still experiments that are not easy to do. And there's still a lot of work to be done. So just to finish with, of course, in the field, there's astronomy on one hand, and there's modeling, and there's nuclear physics on the other hand. And we need to do our best to provide the best input in order to understand and answer these questions about stellar nucleosynthesis. And so in the US, the next generation rare isotope facility is currently under construction right here at Michigan State University. This is a big project by DOE Office of Science and Michigan State University and the state of Michigan. And it's getting close. We're only maybe a year and a half away from completion. So the whole community is very excited to use the new capabilities that FRIB will produce to answer one of the big questions we're trying to answer. It has to do with stellar nucleosynthesis and the R process. So to wrap it up, I just wanted to go back to the original paper B²FH, where it brought together the expertise coming from different fields. And this is what's unique about the field of nuclear astrophysics, that you do need the expertise from all different subfields. And of course, Margaret Burbidge was the observer, and she brought a lot of this abundance distribution and the different observations and how to interpret this. And this is still happening today in the nuclear astrophysics community. We all come together, and the experiment that I do with the model that someone else, one of my colleagues are doing on their own, they're not as useful, but when we work together and we put everything together, obviously we are the strongest. And this comes already from the B²FH work. Thank you.
Artemis, thank you so much. And next up, Anna.
Yeah, hi everyone. Let me share my screen. Okay. All right, I hope folks can see this. I am really humbled that I've been given the chance here to talk today in this online session where we commemorate Margaret Burbidge and her work. I'm one of her scientific granddaughters, so to say. And same as Amanda, I've only met her once at this meeting in 2007. I'll say a word about that in a moment, but I want to really connect the nuclei to the cosmos again today, threading in what she has started and how we are finishing and continuing this, because it's an ongoing story, and we have to keep telling it. So same as Amanda, we met her at this conference, 50 Years of Nuclear Astrophysics, and it was really a grand moment in my career. I was a young, ambitious postdoc at the time, and you can see a photo there of me and her at the conference dinner. It was really hard to catch her, and I only got maybe 2 minutes with her in between all the noise. But it left certainly fond memories, so much that I actually wrote about it in my book. So this is the photo that got published in my book, because, as I said, that was a once in a lifetime opportunity. And the rest of my talk is really a reflection of some of our latest science results that I would have liked to discuss with her. And so in the spirit of that, let me say that yeah, here is the big famous paper, 1957, the synthesis of the elements in stars. And Margaret and her colleagues were asking a lot of questions, how elements are made. And they listed all the nuclear synthesis processes there in this table of contents, and specifically about the hour process. And we've fortunately already heard some introductory words on the hour process from Amanda and Artemis. But they were asking for observational evidence, and they say here observational evidence could be obtained only by interpreting the spectra of type 1a supernova, or I interpret that to be type 1a supernova, a problem which so far had remained unsolved. And we've learned a lot more in the last 60 years, but we haven't learned everything. But I'd like to share some updates there, because we have data now. It doesn't come from supernovae as such, but it comes from the oldest stars in the Milky Way. So where are these stars found, and what secrets do they tell us? Ancient stars that are about 13 billion years old are found in the outskirts of the galaxy, in the so-called halo. And as it turns out, a rare fraction of the already rare ancient stars do contain the signature of the hour process. And actually that should read 150 or so, but so we have done tremendous work over the last few decades, 2-3 decades, with many colleagues, some people's names I've seen in the participants list. We've all been working together to unearth these ancient stars, specifically with this hour process signature in it, because they tell us about this nuclear synthesis process that must have occurred prior to their formation. So they were born with that signature. The challenge with finding these stars in the Milky Way is that we actually don't really know the origin of these stars, because the latest models about the formation of large galaxies suggest that the outer part, so the halo, was actually assembled from accreting smaller dwarf galaxies. So possibly the majority of all these outer stars actually originated in small dwarf galaxies a long time ago. And if we're trying to figure out or learn about nuclear synthesis processes prior to these stars' formation, then we are looking in the wrong place. We've got to look in these small dwarf galaxies. So here's a signature, a chemical abundance signature of one of these hour process stars, the very first one originally discovered in 1993 or 4. I'm sure Margaret was aware of that at the time. So this is just the most prominent one that we know of. And you can see in red all these abundance measurements there. And the blue line is the scaled solar hour process pattern. It is not a connection of the dots. It's a near perfect match. And that's referred to as the universality of the hour process. And it really looks like the stars, no matter when and where they form, they just know what this pattern looks like. They have formed from this gas that shows this pattern. there's not much we can do about that. And so that bears a lot of information that, of course, would have been very important to know for for the B squared of H team back in the day. But as I said, we have data now, and so we continue to explore this. So here is just a graphic representation of the R process. So blue are all the R process elements. This is everything that they ask the questions about. You remember the table of contents, so all the different colors are basically going along with one of their entries in the table of contents in that paper. Amanda also mentioned the S process. It produces the same elements, except for thorium and uranium, through a different process, and it's on us astronomers to figure out through the typical patterns of these two processes to tell like which nucleosynthesis process operated prior to the birth of the star that we are observing. And then, of course, for good measure, I have to throw in the solar abundances here. So for those, it looks a little bit more mixed. It's not a clean signature. The sun is a process formed from gas that had been enriched for about 8 billion years. So it's very messy. It bears information as well, but it's much harder to extract that. And of course, once you get into all the isotopes here of all the heavy elements, then this is how you get to the, through a long story that I have to cut short right now, but you can get to the solar R process pattern, which is the pattern that people have used all along to try to study the R process and other processes to learn about element formation. So I want to spend a few minutes on a little dwarf galaxy called Reticulum 2, because as I said, the halo R process stars actually may not be the best ones we want to study when we want to learn about the origins of these heavy elements, because these stars are just the tools. They just preserve the signature. They're not responsible for it themselves. And here is a couple of pictures actually of this little dwarf galaxy. On the left, all stars in the direction of it. If you take all the foreground stars out, you are going to be left with just the few dots on the right. If you can't see anything on your screen, that's okay, because there's really not much to see. So you then understand why this is called an ultra faint dwarf galaxy. Only a few thousand stars that make up this galaxy. And together with my former grad student, Alex G., we also went to the telescope, the Magellan telescope in Chile. Well, actually he went. I stayed home with my baby that I had at the time. And he took all these spectra, very ratty, probably, you know, about the same bad quality as what you would get observing a QSO with a small telescope. But when there's a signal, and you're gonna see it. And this is the takeaway message here. You can see along the blue dashed lines that even in the ratty data, you can see lines in most cases except for two. So we have found that most stars in this little dwarf galaxy are actually R process stars. And now they are in a dwarf galaxy, though that provides us with superior information because, well, first, I have to say, we of course studied the abundances, and here it's plotted on the scaled solar R process pattern. In purple, you can see the scaled patterns, and they match the black dots, the data perfectly, even in the case where we only measured 2 elements at the bottom right. But this galaxy, Reticulum 2, is an R process galaxy, and what a triumph that was to find a system where we could study the origins of this nucleosynthesis process that gave us all these stars. I'm not entirely sure why my screen, here we go. Let me share again. All right, now it works. So we asked ourselves the question, you know, we have this R process star in a dwarf galaxy. What can we learn from that? What can we quantitatively derive? And so we could estimate for the first time the dilution mass into which an R process yield would have been diluted, again, to later on pop out a generation of R process stars. And we bracketed that to be between 10 to the 5 and 10 to the 6 solar masses. And then we went ahead and did our calculations with 10 to the 6 for good measure. And we took an R-process yield of 10 to the minus 4 solar masses of europium. So this is just for europium, one of the most prominent R-process element. And if you imagine that you're dumping that sort of amount of europium into 10 to the 6 solar masses of gas, then you get a europium over hydrogen abundance of minus 1.2, and that should be the abundance of that next generation of stars. So if we compare that minus 1.2 value with our observations, then I'm just going to cut to the chase here. Then this is what you get. So on the right side, you have europium abundances, on the left barium. So we did the same thing for barium as well. And you can see that the value of minus 1.2 is sort of in the middle of this orange bar. It has a plus minus 1. This comes from the gas mass uncertainty. That's a 1 dex up and down. And you can see that this bar nicely covers all the red data points that are reticulum 2. I should say that all the other colors are other dwarf galaxies, and in gray, that's the background, are the halo stars, R-process halo stars and just normal halo stars. And you can see there are a number of gray points underneath the red reticulum stars. So these are the halo R-process stars. So they look at face value identical, as they should, because they're probably all originated from little dwarf galaxies very similar to reticulum 2. But without actually having at least one example of these stars in a dwarf galaxy, it's really hard to make that sort of calculation that I just presented to you. Now, the big question is, what is, this R-process event? Actually, I have purposefully avoided to name it, but of course it's written there on my slide. We assumed that this would be a neutron star merger. And it is not unlikely that it was a neutron star merger. This is ongoing research. And Artemis has already given some introduction about the recent gravitational wave results. I want to believe that it's a neutron star merger, but it could also have been an unusual type of supernova, perhaps, so we cannot entirely rule this out, but we can place a constraint on the yield. And so that's the exciting part. So here is an example or if this event would have been a neutron star merger, then here are a few numbers. So the total yield across all the heavy elements would have been 10 to the minus 3, 10 to the minus 2 solar masses. We did our calculations for individual elements because, again, that is what we can observe. Neutron star mergers are not without problem. They can easily produce all the elements heavier than barium, but it just takes a really, really long time for them to in-spiral and eventually, become, merged. And the question is, wouldn't that maybe have taken too long in a small system like reticulum 2? But the minimum in-spiral times are set at about 100 million years. So maybe we were lucky and found a system where there was one of the much faster neutron star mergers there. So there's much more to discuss and to learn on that front. And I'm very excited to participate in that. So I'd like to finish my talk here. Oh, here's some more information, yes, with a letter to Margaret, to summarize. Dear Margaret, I only met you once, very briefly. It was a profound highlight of my career that I will never forget. I was that eager young postdoc talking about the R-process and the oldest stars. You listened with curious interest. We agreed that there are still many open questions regarding element production. I would have liked to get to know you better, but be assured that I will continue on our path of answering the many, many questions about the synthesis of the elements and stars. With heartfelt gratitude and appreciation, Anna.
Thank you, Anna. You want to, there we go. Thank you so much. And polishing off, Nicole. Anna, you want to stop screen share?
Okay, so first I just want to thank all of the speakers for those excellent talks that preceded mine. It was an honor to be part of organizing this event for Margaret, and it's an even bigger honor to give the final talk here with a forward look on the R process from a junior person's perspective. I'm going to try to couple together a little bit of what we've already heard from Anna and Amanda and Artemis here from the perspective of a young theorist. So, okay, I have to click on it. Okay, so we've already heard about this. We're very aware of this, that the B squared FH contribution was to be able to look at what we see within our sun and say that there had to be many processes which produced this and study them each quantitatively. So many processes, many sites have enriched our solar system. So on the right, you can see something that Artemis has already mentioned, that all these different types of processes operate in different regimes of the nuclear chart. And with respect to B squared FH, there are more, as both Amanda and Artemis mentioned, there are more now that we understand to be operating than there were mentioned at the time of B squared FH. However, what I will focus on is one that was mentioned in B squared FH, the R process. It's an area where there's still a lot of work to do that goes through this unexplored territory within the nuclear chart. So as also was previously mentioned a bit, the site at which our process was previously thought to occur is within supernovae. However, more recent simulations have found that you cannot obtain the conditions that are required in order to make most of the heaviest R process elements past a mass number of 130. There are different processes that could be in play in supernova, such as alpha N or nu P, which can reach what we call the lighter heavy elements or the weak R process up to a mass number of 100. But nevertheless, we're not getting the heaviest elements out of these systems is what's believed from current simulations. So more rare types of supernova events, things like magnetorotationally driven supernovae, collapsar disk winds, have the potential to reach the heaviest elements. But again, simulation and calculations are different between different groups. These are active areas of research, and it's unclear as to whether or not these rare supernova types of events do make the heaviest elements. So there's still work to do here. So the event was also mentioned, this gravitational wave event from a binary neutron star merger in the electromagnetic spectrum that was observed following that event. But here I just wanted to give a little bit more of a visual as to how we have evidence for this. Why do we think that our process elements, heavy elements, were produced within this type of environment? So spectra and light curves depend upon the nucleosynthetic content of the ejecta. And down here you can see a couple of different light curves and the different observational bands that were observed from this event. So why this is significant, why this type of observation is significant, is that if you have heavy lanthanide elements here, the opacity of your material will increase, and then your light curve will shift to be a longer duration light curve towards the infrared. So you can see that explicitly here. Things in the blue were occurring early. You can see this even more explicitly and intuitively from this figure here, early blue signatures, followed by later red signatures coming from this event. So this is our evidence for lanthanide production within this event. However, I want to point out that this is just evidence for lanthanides and not necessarily anything beyond. Gold and platinum live within the third R process peak, and the actinides are even further beyond. So what we have is evidence that lanthanides were produced due to high opacity. It could be a combination of lanthanides and actinides or just lanthanides. There remain open questions as to the exact reach of these systems. Okay, so even focusing on lanthanides, can mergers account for all of the lanthanide material observed within the galaxy? There were 2 works that were published recently after the merger event that suggest that this is still very much an open question. So on the left, what we see here is calculations of the neutron star merger rate that would be required in order to produce all of the europium that we see within the galaxy, as compared to the rate interpreted from the LIGO-Virgo gravitational wave event. Now, if you want to do this, you can't just assume that mergers make a solar type R process. So we do these types of calculations from first principles, putting in the nuclear physics rates like Artemis mentioned, and we see that we have a spread based upon nuclear physics uncertainties. We're going through this uncharted territory. So those uncertainties propagate into things like this, where you're trying to interpret whether or not a merger would make enough in order to produce all of the lanthanide material that we see. Additionally, on the right, a distinct different argument that's still with europium is if you look at the disk, you see a trend within the stars that goes like this. Now, if you do a galactic chemical evolution calculation where you try to take into account that it takes time for neutron stars to find each other, then this is the type of trend which you get. And again, this is the rough trend that you need. So this is indicative of potentially an earlier source being needed in order to explain the European content of the solar system. So that was about lanthanides, but what about actinides? So interestingly, supernova light curves were stated to potentially have a connection to an actinide element, californium-254, in a work that included the authors of B²FH and another one, RF Christie here, where they noted that this long half-life of californium and the energy production from spontaneous fission of this actinide could influence the light curves. Actually, it could be driving the light curve of a supernova event. Well, now we know that that is connected to the decay chain of nickel and not californium-254. Additionally, we know, as I mentioned earlier, that supernova simulations don't really support production of the heaviest elements, but mergers might. So in a paper put out by our collaboration, we took a look at whether or not we are producing californium, and indeed we are. And we also propagated this through to a kilonova light curve calculation to show that at late times, you can indeed see potentially a signature of californium, but this will depend upon how californium is populated, which is influenced by all those nuclear physics unknowns, including the fission. So there's open questions and work to be done here. But interestingly enough, here we are again, following in the footsteps of B²FH authors and rediscovering the things that they developed in the context of their work over 50 years ago. Okay, lastly, I wanted to discuss that the approach of taking a look at features in the abundances to indicate something, to learn something about your heavy element synthesis is still a very active area of research. So I like this quote from B²FH that I have pulled here. It has generally been stated that the atomic abundance curve has an exponential decline to A of 100 and is approximately constant thereafter. Although this is very roughly true, it ignores many details which are important clues to our understanding of element synthesis. So the example that I will use and how we're still using these features of the abundances to try to infer the enrichment of the solar system is this little peak here, the rare earth peak, that lies between the second and third peaks connected to those shell closures that Artemis mentioned. And the rare earth peak is a feature of uncertain origin. It could come from something like neutron-rich lanthanides having deformation and therefore making the region particularly stable. Or it could come from fission deposition as you go up and then you deposit into the region based upon your different ways that the nucleus can split. You could in principle produce such a feature. So those are open questions as to how it's produced, which means that this is intimately connected to the astrophysical conditions that are producing it. Is it a fissioning type of condition? Is it a condition that runs through the region where you have deformation in such a way that you can form that peak that would match solar data? So once you start to pin down the nuclear physics, you can connect it back to the astrophysics, because these work hand in hand, and say something about the enrichment of the solar system. So as Artemis mentioned, there are upcoming experiments that will probe the neutron-rich regions much further than we have previously. And as Anna mentioned, more and more stars are being observed. So we can take a look at the details of the patterns here of such our processed enhanced stars in order to learn more about heavy element nucleosynthesis. Now, for the last few slides here, I just want to move away from the science and more to the human aspects of why Margaret is an example for young researchers in this field. So I like this quote a lot. "A guiding principle in my life was activated. If frustrated in one's endeavor by a stone wall or any kind of blockage, one must find a way around, another route towards one's goal." So this comes from her memoirs, and it states, and apparently she said this in the context of being turned down for a fellowship due to her gender. I have never known that level of explicit sexism, and I owe a debt of gratitude, myself and other young researchers, female researchers, owe a debt of gratitude to women like Margaret for to a larger degree not experiencing such explicit sexism. However, I do know what it's like, as many women may, to be the only female in the room. So I just want to take this opportunity to say, in recognizing how far we've come, we should also recognize and appreciate where we are now, and that we still have a lot of work to do towards combating gender bias. Additionally, I really like this quote because it doesn't necessarily have to do with gender bias. I see this as speaking more directly towards all junior researchers when they're trying to progress their careers. So with that in mind, my last slide that I would like to show is just a picture of all of the faces who go with the names who were cited in this paper, all of the different works cited in this paper, in this talk, and all of the junior researchers that contributed to such works. So some of these are new staff, new faculty, but a lot of them are postdocs and graduate students as well, and all of their names are down at the bottom. So all of us can learn from Margaret's story and owe a debt of gratitude to people that made a path forward for all of us to be able to contribute to the understanding of the world around us. So with that, I'd like to conclude this conference. I would like to thank all of the speakers for their wonderful talks and remind anybody who's interested that this will be posted. It's been recorded. So if you'd like to pass it along to interested parties, it will be on the website and available. So thanks to all the speakers again, and to everyone for attending.
Thank you, Nicole. And we'll go ahead and end this one.
Thank you, everyone.